gas emissions. He has presented a number of keynote seminars around the world, and I welcome you to this the Remedia workshop. I give you the floor. Thank you.
Muchas gracias. Buenos días. That's all I can say in Spanish. Sorry for this. I would really like to thank Professor Marcandia and Agustin del Prado and all organizers for inviting me to this workshop, and I'm very happy to participate in this event that marks the start of your network on greenhouse gases mitigation in agriculture. I'm very happy that you could assemble this network, and I wish you a lot of success with this scientific initiative. I will try, and this is not so easy, to offer a synthesis of some aspects of greenhouse gases in agriculture and forestry to some extent, and also address mitigation issues. So I would briefly remind you about the climate negotiations and the food security issue, then address international and European research programs, as also Dr. Marcandia has explained. And then I would go on to address the land-based carbon and greenhouse gas balance of Europe. How can we compare the arable, pasture, and forest systems? Have a special point on greenhouse gas balance of grazing systems, and address the balance of farms. And finally, I would say a few words on vulnerability to climate change of those systems. As already explained by Professor Marcandia, we know that the agriculture, forestry, and land use sector, which is, by the way, a new sector for IPCC, but also, to my understanding, for the climate negotiations, accounts for 1/3 of the global greenhouse gas emissions. These are called the non-energy emissions, in fact. And in this respect, there's quite a substantial potential for mitigation. And in the last IPCC report, it was mentioned that presumably a large share of this potential would be through soil carbon sequestration. That's also why today I will address this issue of soil carbon sequestration. However, when you think about the issue, you have very different views. You have the view of the sector, but you also have the view that consumers and companies increasingly push, which is about the life cycle of the agricultural products. If you have a farm here with 1 kilogram of milk at the farm gate, it requires a number of inputs to be produced. Some of those inputs would be traded internationally, like soybean produced in Argentina, say, being shipped and trucked to farm, and this involves lots of emissions, including deforestation. And then you have other inputs like fertilizers that come from the industry sector. So you see that, in fact, when you take this view of the life cycle, you have a cross-sector and cross-boundary view of what happens. However, in the climate negotiations, countries are negotiating on the basis of the sector and on the basis of their own emissions. In 2007, the European Union committed to an overall 20% reduction in greenhouse gas emissions in 2020 compared to 1990. And as you may be aware of, agriculture is committed to a 10% reduction, however, with a variable share of efforts across countries in Europe. Recently in Durban, there have been modest progress in terms of role of agriculture in the climate negotiations. It has been decided that the SUBSTA, which is the scientific and technical body of the climate negotiation, would organize an international exchange of views about the role of agriculture, and this will be discussed further in the Doha meeting. When we think also of this issue, we should remind that there are many perceptions, and livestock, for example, livestock production is increasingly perceived as a threat to climate. This, I think, started mostly with the livestock long shadow report from the FAO, showing that actually 1/3 of the anthropogenic methane is being emitted by the livestock, 2/3 of the nitrous oxide, 9% presumably of the carbon dioxide, this being in their report from deforestation essentially. And since we will have a large increase in food production, but especially in the animal products that are projected to more than double by 2050, we would have severe increases in emissions. And it's funny, I have this ad which was from the International Air Transport Association, and what they say here is really the culprit is the cow, it's not the airplane. Huh? But so that's also why agriculture gets severely attacked. And since consumers in some countries are provided with labels, with food labels, then they have also an opportunity to decide of what they will select. Will they buy some meat or not? And will they be sensitive to the carbon footprint of those products? We have such an experiment in France right now, and it will be interesting to see if consumers are sensitive to those carbon labels. If you take this life cycle approach, there was recently a study organized by the Joint Research Center of the European Commission, and they studied the role of the livestock for the European emissions. Remind you that those emissions are about 5 gigaton of carbon dioxide equivalents. And according to a life cycle analysis, European livestock would account for about 0.7 gigaton of CO2 equivalent, that is 13%. So also in Europe, they comment that the livestock shadow is long, contributes to 13% of the total EU greenhouse gas emissions. You know that, in fact, a lot of the crop production is for livestock. And according to this study, which uses a life cycle approach, livestock would represent 85% of agricultural emissions. And we know that this is, well, substantial part of this, maybe close to 60%, is from the bovine production. If you still expand the scope and you not only consider the life cycle, but also the food habit, the way people behave, you come to this view, which was developed by Tara Garnett from the Food Climate Research Network in UK, where you can see that you have all the changes in the technologies that may lead to mitigation, like anaerobic digestion, nutrient management, and so on. But then you have also possible changes in the food consumption patterns, and this would also be at the post-farm gate, changes in the way the food is cooked, for example, or stored, and how do you reduce waste, and how do food habits change. So all this, in fact, when you take a very broad view, is implied when you talk about greenhouse gas mitigation in agriculture. And we have an interesting study in France, and sorry, there are a few words in French here, but however, this compared the footprint, the carbon dioxide equivalent footprint of men and women. So as you see, women behave far better. they emit less greenhouse gases than men, so that's interesting. But then what is also quite surprising and counterintuitive is that those women consumers, female consumers, that have overconsumption of calories, like eating too much fats and eating too much sugars, they have actually less emissions in CO2 equivalents than those that have a very good diet, you know. So poor food habits could actually, well, that's maybe more a question mark, to lower greenhouse gas emissions. However, the difference is not significant for men. So this, I don't say these are conclusions, these are just sort of preliminary studies, there are still large uncertainties, but it's just to show you that sometimes if you get to this level of the consumer, you may end up with some very counterintuitive findings. And this could be because, you know, if you eat a lot of fruits and vegetables, there is a lot of packaging in all this, and maybe it increases also the carbon footprint. Okay, so this was really sort of broad context. However, there is now, because of those issues, some research programming going on First of all, there is a Global Research Alliance on Agricultural Greenhouse Gases, which was decided by the agricultural ministers at the summit in Copenhagen in 2009. We have here 3 groups that are dealing with livestock first, then croplands, then paddy rice. This alliance has about 36 countries. We have really all the big emitters, I would say, like including China, US, and so on. And you can see here countries which are leading those groups. And we have also some cross-cutting groups, one of them being about the soil, carbon, and nitrogen cycling, and the other about inventories, national inventories, and measurements for inventories. So this is an interesting framework. I would say as a scientist that the only problem is that it's not funded, so you have to see how you can participate on rather a voluntary basis, but it provides lots of opportunities for collaborations. Now we have launched this joint programming in research on agriculture, food security and climate change, and we have 21 countries in that one. We have 5 core research themes in the FACE JPI, Joint Programming Initiative, and here is the scope that we have undertaken in the Scientific Advisory Board of the JPI. It could be of interest because we try to have some different aspects related. You see that on the one hand there is clearly a need to improve the national inventories. This means that you need to have monitoring, reporting and verification frameworks, and if you want to have policies you will need to verify the decline in emissions. I will talk briefly about an infrastructure that can help for this. On the other hand, you have to think about how the consumers may change their habits, and there you need the life cycle analysis methodologies. But if you want to understand the full system, you need to develop storylines and scenarios of what will happen in the future to help develop policy options. You need obviously the technical measures for mitigating, and then you need to understand how farmers can incorporate those measures at the farm scale through changes in their farming systems. And this is obviously very difficult. And how would you relate all this? That's still a question mark to me. We somewhere need a conceptual framework to bridge the gaps between all those elements and try to have a substantial understanding of the system involved. I was mentioning ICOS, which is an infrastructure for a carbon observation system. It's a large European infrastructure that is funded by several countries under ESRI, which is the high-level European system for research infrastructures. It has an ambitious goal, which is to bridge ecosystem models, atmospheric models, with inputs from remote sensing, from inventories, from terrestrial and ocean in situ networks, measuring fluxes, for example, and using also emission inventories. And it should deliver some human and natural greenhouse gas emission maps for Europe, for sure, but also at a smaller scale for regions within Europe. And the objective would be that you would just be able to log to a map that represents emissions over the last months, maybe in the Basque area, for example, and you would see what has changed and where do the emissions or removals come from. So an ambitious infrastructure project. Now I would like to mention ANAE, which is Analysis of Ecosystems, also an ambitious infrastructure system, also under ESRI, which will presumably start soon. And it has the idea of having studies of ecosystems, both in situ and in some more controlled facilities with help of analytical platforms and also of computing platforms. And this at the ecosystem or agrosystem level is really the sort of tool you would like to have to understand the complexity of why you get emissions or removals. Now we have the animal change project that I'm coordinating, and I would just say a few words about it. It's about the global and regional livestock, and we want to understand interactions between livestock and climate change. So we want to develop storylines and scenarios to have a detailed assessment of mitigation and adaptation options for Europe, but also for Brazil and from regions in Africa. Understand the technical potential for mitigating and adapting to climate change, the economical potential, the barriers to implementation, and have quite a lot of modeling in this. You see the partners here. Partners outside Europe are in New Zealand, but there are also in regions in Africa, like South Africa, Senegal, Tunisia, and also Kenya. And now we have partners also in Brazil. As I mentioned, we are trying to assemble some emissions storylines, and it may be interesting to go back to what happened since 1970, and this is the global livestock sector, and these are calculations we made recently about direct greenhouse gas emissions from livestock. So you see that the animal food production has been multiplied since 1970 to 2007 by approximately 2.5. But then the global emissions of greenhouse gases that we could back calculate were multiplied by a factor which is lower, about 1.8. Therefore, emissions per unit animal food protein have been in fact declining. So the major drivers of this is first that we have a reduced use of red meat and of milk, well, no, maybe not milk, but at least of red meat, as compared to pork and poultry. And pork and poultry, they emit less greenhouse gases per unit animal product than the meat sector, the red meat sector. And then we have also increased efficiencies in the production systems. So I think it is interesting to have this in mind also. However, just remember that the emissions per unit animal proteins are far bigger than per plant proteins, obviously. And that's what you can see on this slide. Also, you had a decline. They are still much higher than emissions per unit plant protein. And that's a mean of both at the global level. Okay, I would now go to a more detailed scientific presentation of those issues, trying to synthesize the outcomes from the Carbo Europe and to some extent Nitro Europe projects. My view would be that we have still a lot of uncertainties and we need to reduce uncertainties. We know in the inventories of the enteric fermentation, of the manure management, of the nitrous oxide emissions, of changes in forest carbon stocks, in soil carbon stocks. However, we are still having in the national inventories big uncertainties. How do emission factors vary? They can vary over time from one year to the next. They can vary across farming systems, and this is not captured by the inventories. How far is there a role of climatic variability for greenhouse gas emissions and removals? Are soils sources or sinks of carbon, even under constant management? This may sound as a funny question, but just remember the environment is not in equilibrium. We have global climate change, and this means we have increased atmospheric carbon dioxide, we have warming, and ecosystems may react by either removing more carbon from the atmosphere or releasing more carbon. We have to understand all this. As I said, on a global scale, land and oceans indeed store carbon. If you compare the emissions since 1960 from fossil fuel combustion and from deforestation, that is land use, here you see that obviously there has been a large increase in CO2 equivalents. We are now above, well, in 2007 we were above 8 gigaton. Sorry, this is petagram carbon per year actually. However, the fate of this carbon is partly through accumulation in oceans. We have a large sink of carbon in the oceans. We have also a large sink of carbon on the land, in the continental area. However, as shown here, this sink is very variable from one year to the next. Depending on the atmospheric circulation and the oceans, we may have either large removals of carbon from the land ecosystems, or we can have also sources. During especially the El Nino years, we tend to have a loss of carbon from ecosystems, and during the La Nina years, we have a more favorable situation, and we have a lot of carbon sinks on the continents. So the Carbo Europe project was basically to understand a bit this at the European scale by combination of upscaling for prediction and of downscaling for verification. And you see also the combination of measurements, and indeed quite a lot of modeling was linked to those measurements. The main result, I would say, is that the project was able to produce this map which is the land-based carbon sequestration in Europe. You can see here that in the blue colors we have a carbon sink. This is a mean over 2000 to 2004. However, in some parts, and I must say this apparently is the case for Spain, but however there's a lot of uncertainty, it's possibly not really a sink, and in other areas you may even have a source of carbon on average. So where does the carbon go in those ecosystems? Obviously it goes into the forests, but it goes also into the soils. And as I said, there is a lot of uncertainty. You can view it on this map. And those measurements were actually from atmospheric inversion of carbon dioxide gradients, but they are quite confirmed by the ecosystem data also. Now we can see here that if we turn to the land-based greenhouse gas balance, including carbon sequestration, but also including the methane and nitrous oxide emissions, especially from the agricultural sector, you see that we shift from a sink to a source, especially in those countries with high agricultural emissions, like in Netherlands, in parts of Spain, in parts of Italy, and also France or UK. Then we have so much nitrous oxide and methane being emitted that it largely compensates for the carbon sink. In a summary of those maps, we can say that the land surface sink reaches about 110 million tons of carbon per year, 11% of the carbon dioxide emitted by fossil fuels at urban scale, so it's substantial. However, emissions of methane and nitrous oxide are relatively higher. This means the balance emerges as a greenhouse gas source of 34 million tons of carbon per year. This increases to a small extent the emissions from fossil fuel burning. It's interesting to compare now the arable, pasture and forest systems, and this was possible in that project because we had a large number of flux towers that were addressing forests but also crops, grasslands. And I can remind you about those methodologies. You have here a flux tower over a forest, you have a 3D anemometer, and you have a fast infrared analyzer for the carbon dioxide. And here you can see the seasonal changes in the carbon balance. This is over time. For example, in that forest, it is over time. And this is a daily pattern with the daytime uptake and the nighttime release. And the same can happen for evapotranspiration. And you could compare here a forest, which is obviously a perennial system, with a crop, which is only a seasonal uptake of carbon dioxide, and then during winter you would have only respiration. So if we start to try to understand deeper the components of a managed ecosystem carbon budget, we need to think about the balance, obviously, between photosynthesis, autotrophic respiration, heterotrophic respiration from the soil, and then we have the agricultural management, because we may have cuts, we may have organic fertilizers applied, bringing in carbon. So we have a neat ecosystem exchange, which would be typically measured by a flux tower. And however, what we would call the neat biome productivity, which is the carbon balance of the system, needs to account for all the agricultural management. So if we turn to the balance between gross photosynthesis, autotrophic respiration, and heterotrophic respiration in contrasted European ecosystems, we see here the GPP, gross primary productivity, from the croplands, from the grassland, for the forests. So there is maybe a slight difference. Possibly grassland would be slightly higher. However, what is quite different is also the respiration, and it is again higher for the grasslands compared to the croplands and to the forests. Now, if you take the balance of both, you have the neat ecosystem productivity here, a balance between GPP and respiration, and you see that in fact it's not so high in forest as compared to the agricultural systems. So you may say, okay, we are accumulating more carbon in the agricultural systems. However, what happens is that this carbon, it will be removed and used, and therefore it will be decomposed far quicker than in the forest. And that's where you can now look at the balance between the neat ecosystem productivity, which is here, the addition of carbon through manuring, which is figured only obviously for the croplands and for the grasslands, and the way this is compensated by other losses, the main loss being through harvest, and harvest would happen in grassland and in croplands each year, and only after several decades in forests. So that's a substantial difference, and that's why the forests tend to accumulate more carbon. And then you may have some additional losses, like in the waters, through dissolved organic carbon and dissolved inorganic carbon. And in the agricultural systems especially, you have the nitrous oxide and the methane losses. But if you take this view, you will see that they are, in that slide at least, summarizing for carbo findings, quite small. And if we make the balance, which is this line here, you see that the arable lands, they are actually a source of carbon dioxide equivalents. The grasslands are a small sink, and the forests are a larger sink. Just like to say a few words more about the dissolved organic carbon leaching, because it has been revised to higher values than people expected before. And you see here the good correlation between the dissolved organic carbon concentration in the waters and the C/N ratio of the soil. So it could be that this would help in creating indicators to calculate the amount of dissolved organic carbon lost in the waters. Finally, if I show the details of this terrestrial greenhouse gas balance, we have the forest biomass, which acts as a sink. Now we have the forest soil, we have grasslands, which are also a sink on average, croplands, small emitters, peatlands. They are in Europe a source because they were drained especially. Land use change in Europe is a sink because we have still a lot of afforestation. We export carbon. We have carbon losses to rivers and seas. We have fossil fuel in agriculture, methane, nitrous oxide, and the balance here of all those fluxes indicates a small source on average. Now, if I summarize for the agricultural sector, you can see here that we have large losses through nitrous oxide and methane, use of fossil fuel in agriculture, draining peats would also lead to losses, croplands, small losses, and in fact, in the agricultural sector, it's only the grasslands that are neat sinks and can help, in fact, in reducing the balance of the sector. And why are these things? That's mainly because of the sequestration, obviously. So it would play a significant role in the European agricultural sector. Now I would like to turn to the carbon balance of the grasslands. To remember you of all the possible fluxes we have in such a system, I would not explain all, but some of them we can easily neglect, like fires. We don't really have fires in grasslands in Europe. And also erosion, all those ones are quite small. So the balance we could calculate would look like this, which is basically what I explained. We have the neat ecosystem exchange, then we have small losses possibly of wet soils in terms of methane. We have the agricultural balance of exports and imports of organic carbon, and we have the leaching to waters. Some years ago, we started thinking about this, and this was our first hints about what would be the carbon cycle in a grazed grassland. And we believed at that time that the soil carbon sequestration from the measurements we had could be a small sink. But at that time, we really had only very limited measurements. Then we got the Green Grass project, and we could establish the balance on 10 European grassland sites. And it was interesting to see that there was a good correlation between the carbon sink or source of the grasslands. Here, when we have a positive sign, it's a carbon sink, a negative one, it's a carbon source, and the degree of herbage utilization by grazing and cutting. So this just tells you the less carbon you would use in the grassland, the more is returned to the soil, and this increases carbon sequestration. Well, it's very simple, isn't it? If you don't use the carbon, it goes back to the soil, it may be partly humified, and you get carbon storage. And obviously, we could also see interactions with nitrogen and with nutrients, and you obviously need nutrients to store carbon in the soil, and this is also related to the stoichiometry in the soil. However, if we want to deepen our understanding about the grassland system, we need to see what happens with carbon cycling and how is it related to disturbance induced by cutting. So we had this grassland mesocosm experiment. I will not show all the details, but the result is that in those mesocosms we could see that again, the more cutting we had, the less soil carbon sequestration we got. And there was a negative relationship between above ground neat primary productivity, which was in fact increasing when we were cutting more, but this was still decreasing soil carbon sequestration. Then we applied steady state 13C labeling, 13 carbon dioxide labeling, and we could see also that disturbance by cutting was changing the mean residence time of carbon in the soil. So you have really changes in the full system. The carbon, when you cut regularly your grassland, is going to stay only 22 months as compared to more than 30 months with infrequent cuts. And we got to some extent some understanding of the system by studying the plant traits. Plant functional traits in grasslands are powerful drivers of the carbon nitrogen cycle. And in this example, we were able to relate the changes in carbon sequestration partly to the changes in the root tissue density. So this tells you that when you change disturbance, you have direct effect on the carbon cycle, and you have also a trait-mediated effect through changes in the root tissue density and hence in the way the roots are decomposing in your soil. I will just show one more slide on such complex issues that relate the plant traits and the carbon cycle with also the soil microorganisms. When you have disturbance, you first reduce photosynthesis and root biomass, but then you have changes in the soil microbial community, you have a decline in the fungi, increase in the gram-plus bacteria, and this accelerates the decomposition of old soil organic matter. We can say it is old because it was not labeled during the experiment. And then it increases also through the acceleration of decomposition the N available for plants in the above ground production, and this changes species composition. So you see that you have many complex interactions in such systems, and in fact it's also possible to have such interactions also in the cropping systems. Another sort of interaction which is quite complex is that you may think that if you modify the management of grassland, you shift it from intensive to extensive, and we have done this since many years now in one mountainside in central France. You would shift the carbon and greenhouse gas balance every year in the same way. Well, that's not true, because look here, we have oh sorry, it doesn't show up very well now, but we have the extensive site and the extensive field plot. This extensive field plot has a greater carbon sink in most year, and however, when we have droughts, severe droughts, we have the opposite. So we have an interaction. The extensive management sequesters more carbon in wet years, but is less resilient to drought than intensive management. So this also shows you the complexity. We have carbon to water interactions and interactions with management. I will move quickly now to some other results where we compared the balance of a number of sites to model it. And I show this very simple model because I've been trying for some time with all the Carbo Europe results to apply some more complex models, but they really failed. So I had to develop a simple model and to fit the model to the data. And you see here we have very simple model where carbon cascades from one compartment to the next. You have few parameter values, and these are the measured fluxes, these are the modeled fluxes. And what was very interesting to me is that we can show with this that the turnover of the slow carbon pool, you must admit it is linked to the nitrogen. This means that the turnover rate of the slow carbon in the soil declines with nitrogen availability. This is very consistent with the priming effect hypothesis, and we can show that it is occurring across the sites we have. So with this model, we can really have a good prediction of carbon sequestration in those sites. And this helped to now upscale. But to upscale, we also need to understand the fate of the carbon that is harvested so all the emissions at the barn. We did those calculations using IPCC Tier 1 methods. And in this way, sorry, the slide doesn't show very well, but we could calculate the carbon balance of European grazing systems. And you see that in some regions, interestingly also in this region, you have a substantial carbon sink according to those calculations. And if we shift to add the methane and nitrous oxide emissions, we turn to the red colors, meaning we get emissions rather than removals. However, in some places, and including, according to those calculations, in your area, we would have grazing systems that are quite extensive. They do not emit much methane and nitrous oxide, and those grazing systems, they would be possibly neat sinks of carbon in CO2 equivalents. Finally, a few words about the farms. When we think about farms, we need to think about how to mitigate. I'm sure you will deal about all this, so I will not expand on those mitigation options. And you need also to think about the costs and benefits of mitigating. And you know that this method is being increasingly used to compare mitigation options. It is about the marginal abatement cost curves, whereby you can have projections of your budgets and you try to abate through a number of mitigation options. And you see here that some options, they may have negative costs, so actually in terms of economy, they could be applied with no extra cost, in theory at least, and some other options, they would come at a high cost, so they would not be applied until you really get to the end of the mitigation potential. However, if you want to know how you need to apply this in a complex farming system, you need to relate this to the system itself, and that's an animal farm, livestock farm, where you see all the emissions that may come from the complex system, linking inputs with the housing, with the animals, the pastures, the meadows, the arable crops, the stores, and so on. And what we have started, but I know there are some other interesting models also, is to develop such models to try to see how you could change the farming systems. And when we did this, we could see that farms are sources, usually, obviously, although you have a carbon sink in the grasslands. Finally, a few words about vulnerability to climate change. To remind you that we have some severe droughts and some severe heat waves. That's just the example of the summer temperature anomaly in July 2003 in Europe that led to a large decline in neat primary productivity of the vegetation. And we had then, this change was recorded with the flux towers, and we could see that there was a large loss of the ecosystems in terms of carbon. Now we are investigating in Carbo Extreme something a bit different. How would an extreme climatic event have knock-on effects on all the system? Not only direct knock-on effects on photosynthesis, but you can also, here it is for a forest, have reduced reserve, xylem embolism, frost, you can have reduced foliage, pre-mortality, wildfires, and so on. And I always like to show this slide because it was in eastern France during summer 2003, but I think you would not guess this was taken in France. We have annual variability. This also modifies agricultural management, and in turn it can modify the greenhouse gas emissions. So we will need to understand all this complexity. And we had a number of experiments recently combining rain exclusion, warming with passive or active infrared, and trying to understand how this impacts not only on the productivity, but also on the carbon cycle, on the greenhouse gases. And just an example of possible adaptation to climate change. Here you basically have the end of a heat wave. So after the heat wave, everything was apparently destroyed. But if you see the temperate cultivars, they did not recover, but the Mediterranean cultivars, they did recover. So there is a possibility here to preserve the carbon cycle by adapting, by using more Mediterranean cultivars. Okay, conclusions now. Soil carbon needs to be accounted for to achieve a consistent greenhouse gas balance in the agriculture, forestry, and land use sector. I think forestry, until recently, has attracted more efforts, but is vulnerable to climate extremes. Soil carbon sequestration requires advanced verification methods, which are still lacking in real farm conditions. There are multiple trade-offs between agricultural production, carbon sequestration, nitrous oxide and methane. We will need to shift the agricultural system gradually in the European regions. Maybe the mitigation strategies will need to be based on an idea of eco-efficiency, that is reducing the emissions per unit of food or feed or fiber product. However, we have large uncertainties, and I think these uncertainties increase when you consider long life cycle or food supply chains. Maybe decisions should not be taken on the basis of life cycle analysis only, because uncertainties are very big. And finally, we should think that if we want to use carbon, it should be sustained over several years or decades, and therefore we need to combine mitigation and adaptation to climate change. And there are also trade-offs with food security, land use and biodiversity. This is what we try to address, and this is one example is the Animal Change project, where we try to combine mitigation and adaptation to climate change. Thank you.
Some questions? Can you ask people if you have any questions? Thank you very much for very interesting and wide-ranging coverage of this material in this terrestrial carbon management. Are there any questions? We have a few minutes which we can take some questions. You are happy to?
Oh, sure. Mm-hmm.
Yes, please.
Thank you, Jean-François, for a very illustrative presentation. You have emphasized the importance of grazing systems as carbon sequestration and the carbon sequestration role. And you have showed a very interesting slide at the end on adaptation of Mediterranean adapted plants. Are you aware of any plant breeding programs on trying to increase the role of carbon sequestration in grassland systems in different weather situations?
Yes, thank you. Yes, indeed. Well, there are different approaches. I'm not sure they are so successful yet, but there are approaches. One is to use high sugar grasses. That's especially colleagues in UK developing this. And in this way, they hope to reduce the methane emissions from enteric fermentation. Another approach would be to use some deep-rooting species, deep-rooted plant species, grass species. And in this case, you would hope that you would have less decomposition of this carbon derived from the root system in the deep soil, and you would build up more carbon. Here again, it has been showed to some extent with the C4 species in tropical context. I'm not sure it has been yet proved to be successful with temperate grasses. So that's one area we need to understand. And however, I would just like to emphasize that we need to get much better understanding of the soil microbial ecology. If we don't understand those interactions, we cannot control the system.
Thank you. This question right at the back there.
First of all, I would like to thank you for your excellent presentation. I like it a lot. I have a question because we have worked on it before, and I would like to know if in those models that you developed, you take into account, or you think that should be taken into account, the carbon sequestered by the different soil particles, like sand and so, because the time of the period of time which the carbon is storage is quite different. So,
sure. Yeah, sorry, I didn't have time to show the details of the model and so on. But indeed, there are some differences with the soil texture. What we did was really to try to have a calibration of the model with the flux measurements, and that's something a bit new in some way. And what we got as a result is that the stabilization of carbon is controlled by the texture, and in our case at least, it was the silt fraction which was playing the largest role. So you got more stabilization when you got more silt.
Some more? Yeah. No? Yes, one more over here, please. Sorry, microphone, please.
I just want to know what is your position about the role of organic farming, the organic management in terms of the Durban decisions and so on. We talked yesterday about this a little.
Okay. Well, first of all, I'm not so sure about what will happen with those exchanges of views across countries and so on. Then about organic farming, I think there is, there are some positive aspects, and one is obviously that the organic farming, it recycles more, so you have usually less losses. And then you have a lower intensity of agriculture, so this leads to less emissions in terms of nitrous oxide and methane. So usually if you make calculations per unit land area, you will find that organic farming behaves better, it emits less. However, if you get now calculations per unit product, sometimes it's the opposite, just because you don't produce so much. So we are still in between, and it's a big debate because you have different views worldwide. You had some papers, including in PNAS, for example, saying because we have been intensifying agriculture so much, we have been avoiding tropical deforestation, and this has helped in reducing global emissions substantially. So that's one view. Then there is another view, which is to say we would need to reduce emissions in agriculture by reducing the intensity of agricultural production, and we will find a way to share the land between agricultural production and ecosystems. So you could have agroforestry, you could have different ways. For example, they are developing this in Central America, where they combine food production with forest systems, with low emission pathways, and this would be also an alternative. So obviously I don't have the solution, but it's a good question.
I think we can close this session now. Thank you very much once again, and we pass the floor.
Okay, just one more thing in English, that to mention that Jean-Francois is going to stay for as long as he would like. His flight is at 8 o'clock, but he's going to be around for some time, so you can still make some questions to him, and he can actually as well have some feedback to whatever we are talking here. Bueno, y ahora voy a pasar a